This is Chemistry Podcast 8.6, and we're going to talk about gas stoichiometry. So the first thing is we're going to quickly review Avogadro's principle. We talked about it when we did the ideal gas law, and we also used it in the lab that we just did. But Avogadro's principle, he found out that at STP, 1 mole of any gas has a volume of 22.4 liters. This is helpful for us because we get to use a conversion factor then right here. It says that 1 mole of any gas is 22.4 liters. So this conversion factor will help us out when we're trying to convert between moles and liters. We'll get to use that, and it'll make it a little faster than having to use PV equals nRT every time. Example problem number 1 says we need to calculate the volume that 0.881 moles of gas at STP will occupy. So since they say it's at STP, we get to use that conversion factor we just talked about. 1 mole is 22.4 liters. So just like before, we always start with what we're given, which is the 0.881 moles. And then it just takes one step to go from moles to liters. This one, I'm going to put the mole on the bottom, and the 22.4 will go on top. I do that so that my moles cancel. And when I plug that into the calculator, the answer I get is 19.7 liters. And that's it for that problem. We didn't have to convert to a different gas, so we didn't have to use a reaction. We just used Avogadro's principle to go from moles to liters. All right, example problem number 2 has 2 questions. A says, what size container do you need to hold 2 grams of nitrogen gas? Well, first of all, when they're asking for what size of a container, that means volume, which means we'll be looking for liters. And we have 2 grams of nitrogen gas. So I'm going to start with what I'm given. Nitrogen is a diatomic, so I put N2. And just like before, if we're given grams, the first thing we always do is go to moles using the molar mass. So nitrogen is 28 grams is 1 mole. That's the molar mass from the periodic table. And then because I'm at STP, and even though it doesn't say that, we're going to assume that it is, 1 mole of gas has a volume of 22.4 liters. And that gets my grams to go away and my moles, and then I'm left in liters. So 2 times 22.4, and then I divide by 28, and the answer is 1.6 liters of nitrogen gas. Part B down here says how many grams of carbon dioxide are in a 1 liter balloon at STP. So again, at STP, I'm going to go ahead and just write 1 mole equals 22.4 liters. And then I'm looking for grams. So I'm going to start with what I'm given. And because I'm in liters, I'm going to use Avogadro's principle first. The 22.4 liters is going to go on bottom to cancel, and that's 1 mole. And then 1 mole, and this gas is carbon dioxide. 1 mole of carbon dioxide is 44 grams. So my moles have gone, my liters are gone. I do the math, which is 44 divided by 22.4, and we end up with 1.96 grams of carbon dioxide. So these aren't much different than problems that we've done. We're just incorporating this new conversion factor that we can use when we're at STP. All right, we need to talk about coefficients again because with stoichiometry we also use the chemical reaction. This says, what are the 3 units represented by the coefficients? Well, the first one, and the one that's the most common, is moles. So we could read this as 2 moles of hydrogen react with 1 mole of oxygen to give us 2 moles of water. The other way we can read this is particles. And remember, particles can be atoms or molecules or formula units. But this says 2 molecules of hydrogen react with 1 molecule of oxygen to give us 2 molecules of water. And that would be this particle thing. And then the third way that we can use the coefficients is liters. And this is new because we haven't talked about it. But when we have gaseous substances that have a volume, That's also representative of liters, those coefficients. So this can be for every 2 liters of hydrogen that react with 1 liter of oxygen, we get 2 liters of water produced. And this is the one we're going to focus on today, which is liters. That'll be the new part of the stoichiometry that we do. So when we're doing these gas stoichiometry problems, there are going to be 3 different types that we can do, and gas stoichiometry means we're going to use a chemical reaction. So we're going to go from one substance to a new substance. We're going to be changing substances. The first type is a volume to volume problem, and in a volume to volume problem you only use the coefficients. And I'll show you how that works, but you just use the coefficients in the balanced reaction and that's it. You don't have to do molar mass, you don't have to do 1 mole is 22.4 liters. It's just one step, coefficients, and you just set up a ratio. When we're at STP, we get to use the 1 mole equals 22.4 liters. And then when we're not at STP, we have to use PV equals nRT. And we'll talk about each of these individually in just a second. But they're all just a little bit different, and we're going to do a couple practice problems with each type. What you're seeing here, though, is we're taking a look back really quick at that stoichiometry flow chart that we've looked at before. And up to this point, I've said ignore all this stuff down here because we'll get to it later when we are talking about gases. Well, we're there. So this is usually what we do. Right down the middle, we start in grams of some substance and we work our way to grams of another substance. Now, though, we're going to incorporate volume and liters. So you can see that we can go between moles and liters, and that's this gas stoichiometry, moles and liters. And we can do that using PV equals nRT or the 22.4 liters if we're at STP. So this is the new part that we're going to be using down here, the balanced reaction and using PV equals nRT or 1 mole is 22.4 liters. Practice problem number 3 says, what volume of oxygen gas is needed for the complete combustion of 4 liters of propane gas, and assume constant pressure and temperature. So in this question they're asking about the volume of oxygen gas, and we're starting with a volume of propane gas. So because I'm starting in oxygen, or not starting in oxygen, I'm starting in propane and going to oxygen, propane to oxygen, I'm switching substances, which means I need a balanced chemical reaction. And this isn't written for you guys, I just wrote it on mine, so you should copy it down. This is something that we would do first, write it out so that we know what we have, and then we can use it. We have 4 liters of propane, and they want to know how many liters of oxygen it has to react with. So because this is a volume to volume problem, we just use the coefficients and that's it. I'm going to flip back really quickly so you can see the flow chart that we were just looking at. We're starting in liters of A and we're going to liters of B. So all we need is a balanced chemical reaction. We just do that mole to mole ratio using the coefficients and that's it. It's just a one-step problem. So with this one, I start with my 4 liters of propane, which is the C3H8. And all I have to do is just set up the molar ratio. For every 1 liter of propane that goes into the reaction, it needs 5 liters of oxygen to react with. And that's it. That's as far as you need to go with that. It doesn't require molar mass or anything beyond that. So 4 times 5 is 20. Well, so your answer for this one is 20 liters of oxygen. Your volume to volume problems are very simple, straightforward. They only require one step. The other 2 are not quite as simple. They require more math and the molar masses and all of that good stuff that we're used to with stoichiometry. So first of all, at STP, we're going to use this conversion factor. The 1 mole is 22.4 liters. When we are not at STP, we have to use the ideal gas law. And the ideal gas law is the PV equals nRT. It's going to allow us to go between volume and moles. At STP, we use this conversion to go between moles and liters, which is moles and volume. But when it's not there, we have to use the PV equals nRT to go between these two. So you're always going to be solving for V, or you're going to be solving for N. That's what you're going to use this equation for. We're going to start with two example problems at STP. And the question says, what mass of glucose must be broken down in your body to produce 2.5 liters of carbon dioxide at STP? So because it's at STP, I'm going to write 1 mole equals 22.4 liters because I'm going to get to use that. Write the balanced equation first. Well, I've already done it. I put it in so you can look at it and write it down yourself. But it's the combustion of glucose, and I've balanced it out. They're telling me I have 2.5 liters of carbon dioxide, and what they're asking is how many grams of the glucose are required to produce that much carbon dioxide. Because this is at STP, all we're going to do is just one big stoichiometry problem. So I'm going to start with the 2.50 liters of CO2. And since I'm in liters, the first thing I want to do is get to moles so that I can just do regular stoichiometry after that. So the liters to moles, that's where this relationship right here comes in. So the 22.4 liters of CO2, that is the volume of 1 mole of CO2. And then this just becomes normal stoichiometry. I need to switch from CO2 to the glucose. So for every 6 moles of CO2, and that was from the balanced reaction, 1 mole of glucose went in. It does help if you take the time to write in what compounds you have so that you can see things are canceling out. And then I need to go from moles of glucose to grams of glucose. So 1 mole of glucose, if I add all those up on the periodic table, it's 180 grams. And that's it. I'm to grams of glucose, which is what they asked me. So I started in liters. I used Avogadro's principle to go to moles. Then I did the mole to mole ratio, and then I did the molar mass to find grams of glucose. So taking all that, plugging it into the calculator, we get 3.35 grams of glucose. And that's it. So for these at STP problems, it's just one big long conversion after another, and we're going to use that 1 mole is 22.4 liters. This next one's at STP again, so I'm going to rewrite this so we remember to use it. It says when steel wool burns in air, this reaction occurs, and they gave me the reaction right here. What volume of oxygen, so I'm looking for oxygen, measured at 1 atmosphere and 0 degrees Celsius, those are STPs, that's standard pressure and standard temperature, is required to react with 100 grams of iron. So I'm starting with 100 grams of iron right here, and I'm trying to find liters of oxygen. So I'm going to start with what I'm given, and anytime I'm given grams to start with, I want to do molar mass first. And iron's molar mass on the periodic table is 55.85 grams of Fe, and that's 1 mole of Fe. Then I use the coefficients to convert from iron to oxygen. So for every 4 moles of iron, there are 3 moles of oxygen to react with. And then they don't want grams of oxygen, which is where you would be used to going. They want liters of oxygen. So that's where we use Avogadro's principle. Every 1 mole of oxygen at STP has a volume of 22.4 liters. So I've canceled my grams of iron, my moles of iron went away, my moles of oxygen, and I'm left in liters of oxygen, which is what they asked me for. So multiply everything on top, divided by everything on the bottom, and you get 30.1 liters of oxygen as your final answer. So not too bad. Very similar to what we've already done, just this new conversion factor right there to use. Example problem 6 and 7, we are not going to be at STP. And what that means is we're going to have to use PV equals nRT. So in this equation it says, if 5 liters of nitrogen reacts completely by this reaction at a constant pressure and temperature of 3 atmospheres and 298 Kelvin, how many grams of ammonia are produced? Well, the first thing I'm going to do is I want to get out of liters and I want to get to moles of nitrogen so that I can do regular stoichiometry. But I can't use 22.4 liters as 1 mole because I'm not at STP. So what I'm going to do is I'm going to do PV equals nRT, and I'm going to solve for the N because N will be moles of nitrogen, and then I can start my regular stoichiometry problem. So the first thing is PV equals nRT. And the pressure they gave us is 3 atmospheres. The volume is 5 liters. I don't know N, that's what I'm looking for. The R that goes with ATMs is 0.0821. And the temperature is 298 Kelvin. When I do that, I see that N equals 0.613 moles. And since I put in the volume of nitrogen, I get moles of nitrogen out. I can't change substances when I do PV equals nRT. So since I put in liters of nitrogen, I'm going to get moles of nitrogen out. This then becomes my starting point for my stoichiometry, my dimensional analysis work. So 0.613 moles of N2. And then I'm going to use the balanced reaction to go from N2 to ammonia because that's what they're asking me to find is grams of ammonia. So for every 1 mole of nitrogen that goes in, 2 moles of ammonia come out. And then 1 mole of ammonia, if I add that up, a nitrogen and 3 hydrogens, is 17 grams. And my moles of ammonia go away, my moles of nitrogen go away. I do all of that math and we get 20.8 grams of ammonia. So we used PV equals nRT to change to moles, and then my moles became the starting point for my stoichiometry problem. This is different than the STP one because we wouldn't have had to have done this. We would have just started doing the 22.4 liters as 1 mole. But since we're not at STP, we don't get to use that shortcut. All right, last problem. Determine how many liters of oxygen gas are needed to combust with 10 grams of methane at 300 Kelvin and 8 atmospheres of pressure. These are not at STP conditions, so again, I'm going to have to incorporate PV equals nRT when I'm solving this problem. You need to make sure you have a balanced chemical reaction. I'm starting with 10 grams of methane and they're asking for liters of oxygen. So how many liters of oxygen do I need? This one is going to be worked backwards compared to the one that we just did. I am going to get as far as I can to oxygen, which means I'm going to start with grams of methane and I'm going to work my way to moles of oxygen. Because moles of oxygen I can plug in here and I can come out with liters of oxygen, which is what they want for their answer. So I start here, I add up a methane and it adds up to 16 grams in 1 mole. Then I use the coefficients in the balanced equation to switch from methane to oxygen. 1 mole of methane goes in, it reacts with 2 moles of oxygen. And I stop there. I can't use 22.4 liters on top is 1 mole of oxygen. That would be if it were at STP, but it's not. So 10 times 2, and I divide by 16, that gives you 1.25 moles of oxygen. Now I can take this, that's my N in PV equals nRT, and I'm going to solve for V, which I don't know. So pressure they gave me is 8 ATMs. I don't know V. My N is the answer I just got. The R is the same R that we just used because it's still atmospheres for pressure units. Temperature is 300 Kelvin. I do all of that, and my answer that I get is 3.85 liters of oxygen. And that is my final answer. So in this one, we had to do the stoichiometry stuff first, and then we did PV equals nRT last. So it just depends on the question, what they're asking you, what you're given to start with, whether you use PV equals nRT first or last. And then also it depends if you're at STP, whether you can just use the shortcut of 22.4 liters in a mole. But that is it for gas stoichiometry. So make sure that you wrote down all those example problems. We are going to do much more practice with these in class. We'll get practice identifying at STP whether they're not at STP, and then also the pathway that you should take to solve these, because that takes some practice in order for you to know what steps to do and in what order to do them in.